Okay, so it's a lifelong number. Just so it works here. Okay, and
sampling.
Yeah, that was just.
Installed successfully, so it's here. We can try if it works.
Good day to everybody. It's my pleasure to welcome today Dr. Johannes Bieser.
Yes.
Yeah. Johannes Bieser from Chemical Transport Modeling Group, Institute for Coastal Research, Helmholtz Zentrum.
It's an unknown small village outside of Hamburg.
Geesthacht, Germany.
Yes.
Geesthacht. It's always hard for me to say Helmholtz. He will give us a talk today on the Global Mercury Observation System and improvement of mercury models. So please.
Yeah, welcome everyone. I'm glad we have so many guests and hopefully also some online listeners. Today I will present you some work on mercury, and I start with a convenient slide, and I just want to tell you mercury really is an extremely interesting substance, and I hope by the end of the talk you will agree with this. It's not just beautiful and toxic, it's also very special. As you know, there are so many pollutants out there. You have pesticides and you have particles and all these pollutants, but they get degraded, they disappear somewhere, and mercury is different. It's an element. It always stays mercury. We never get rid of it. All the mercury we put into our environment, it stays there. It stays as mercury, and because of its unique chemical properties, it really never stays in any sink. So we never get rid of the substance. So it always sticks to us. And in today's talk, I give you a short introduction to this wonderful substance, and then I present to you the GMOS project I'm working on and which funded the most of this work. And finally, I'll give you some first results on our modeling exercises in the atmosphere and the ocean. And hopefully 45 minutes will be enough for this, but I'm sure you're willing to stay for another 2 or 3 hours. So, yeah, first to say, what does mercury do? Why is it toxic? Mercury accumulates in your system and it deteriorates your brain. So basically, you become dumb and dysfunctional. And current estimates of the World Health Organization is that in countries that rely heavily on fish for their nutrition, it's up to 2 per mil of the children actually are mentally impaired because of mercury intoxication. And now I've shown some examples, some limit values. What are limit values? We're talking about some microgram up to milligram per cubic meter in the air or per liter in seafood, drinking water. These are the limit values. You will see the pathways of mercury in a second. So the question is, where does it come from, the mercury? On our planet, we have huge amounts of mercury deep downside in the lithosphere, and the only real natural source for mercury is volcanic activity, which is a quite irregular source, but it's estimated to be something about 90 tons per year of mercury coming into the atmosphere from volcanoes. But ever since we entered the industrial area and we started to mine things like gold or to dig out fossil fuels and burn them, we are accessing these deep mineral reservoirs of mercury and we're releasing them into the atmosphere. So in total, you can see 2,000 tons per year as anthropogenic emissions as opposed to the 90 tons per year natural emissions. And the main sources really is gold mining, where it's especially in small-scale gold mining in poor countries where people use huge amounts of mercury without any safety precautions. And of course, all the fossil fuels, especially coal, oil, we're burning, which releases the mercury into the atmosphere. So if you see historically, how did mercury emissions evolve over time? You see we have this big peak in the end of the 19th century. This is mainly the gold rush in North America, where they started to use the mercury to wash the gold out of the rivers. And you see here, as fast as it started, it ended again. And you can see the last years, we have an increasing emissions of mercury from Asia. So today, Asia really is the largest contributor worldwide, especially China and also India, to mercury emissions. And this also is quite interesting on a global scale, having emissions first in the Western countries for many years, and now in the Eastern countries, it of course also changes the cycle and the distribution of mercury in the environment. Here's a small overview from a recent paper from Helen Amos from the Harvard Medical School. This is a very interesting work where they showed the global cycle of mercury. So as I told you, we have this natural and anthropogenic emissions, and so we're pumping this huge reservoir. You see 3 to the 10 to the 11. It's a huge reservoir. This is in tons, by the way, into the atmosphere. And from the atmosphere, it can go into soils and vegetation. And if there's, of course, an active exchange with the ocean. And the current estimate is, because as I said, mercury has basically no sink. The only real sink term you see is this really small number down here, which would be a permanent sedimentation of mercury. So it's always cycled between the atmosphere, between the biosphere, the soils, and the ocean, and it always comes back again, goes down again. It's really moving around the system, but not disappearing. And the estimate is that we have an increase compared to pre-industrial times of 7.5 in the atmosphere and around 5 to 6 in the ocean. So we have now 6 times as much mercury in the environment as we had before we started to burn fossil fuels, to dig holes in the earth and start mining activities. And these numbers are increasing, and finally might lead to a big problem with toxic foods, because the main pathway of toxicity is that the mercury in the ocean accumulates as methylated mercury in organisms, and in the end you eat it if you have fish. So don't be afraid, some fish is good, but if you eat tuna every day, after 1, 2, or 3 years, you will get sick definitely by this. So not every day. This is another interesting question now, what happens when we release the mercury in the atmosphere? Where does it end? How fast does it disappear again? And this is a is a box model study from the same group where they looked in box models. If we release a random amount of mercury, we call it 1 year, into the atmosphere, just one big peak, how long will it stay? What's the residence time? And you can see the residence in the time in the atmosphere is about 1 or 2 years, while the residence time in the surface oceans is up to 100 years. And the time it takes for mercury emissions to finally come back to a sink is 1,000 to 10,000 years. So you see it really is a problem that the mercury is not disappearing from our system. And now from this you think, okay, I showed you the changes in emissions on the last slide, and what does it mean if it has such a small residence time in the atmosphere? Can we see that? And on first measurements, actually we can see that. Here you see measurements that's from Mace Head at 2 points, that's on the shore of Ireland. That's actually the longest observation series of mercury, which is done by the analytical chemistry team in our department. And here you see measurements from Cape Point at the south of South Africa. You can actually see that in the last years we start observing a decreasing trend. So we see that the reduced emissions in the US and in Europe, together with mostly westerly winds, you get decrease in the mercury concentrations in the atmosphere. Now, it would be really interesting to know how it looks in other parts of the world, and we'll come to this later in the talk. Now, I'm sorry, I heard chemistry. I always know physicists and chemistry. It's difficult, and I try to use a minimum of chemical talk, but I have to ask you to bear with me for a few chemistry lessons. So what does mercury do? In which forms do we have it in the atmosphere? And in the atmosphere, our main component is elemental mercury, just the element mercury. And typical concentrations in the northern hemisphere are around 1.5 nanogram per cubic meter. So you see it's a substance where we have extremely small concentrations, which means it's also difficult to measure. And now we don't only have the elemental mercury, we also have oxidized species of mercury. And these species, you see, it's really minute concentrations of a few picogram per cubic meter. But so you would say, well, why are we interested in this? And the reason is because it's these oxidized forms that ultimately are responsible for the deposition and are the key factor to describe the exchange of mercury from the atmosphere to other environmental compartments and to understand the cycle of mercury. And you might also ask, why do they call it gaseous oxidized mercury? I mean, don't we know what it is? And the truth really is no one knows what it is. The chemistry is the chemistry actually is still a mystery. There are lots of reactions that are proposed. Some people say, oh, it reacts with ozone. Others like OH, but then OH is it's not on vogue anymore. People say, no, the OH reaction we believed in 20 years, it doesn't happen. Or maybe it does. People think now bromine might be the most important oxidant. So it's really amazing that after decades of research, actually we have only very little ideas what actually happens in the chemistry. And my favorite no more chemistry slide, that's just all the substances we assume that somehow it might exist in the atmosphere and the ocean, and it's really unclear which are the important ones, which maybe only exist in theory or don't play a major role. So that's really a big problem if you want to model some chemistry and you don't know the reactions. That's why we just call it oxidized mercury. And this is the point where I'd like to introduce our project. It's called GMOS. It's the Global Mercury Observation System, and I must say a very interesting project because it has a very strong interconnection between the analytical chemists that do the measurements and the modelers. I mean, most of you, I assume, are modelers, and you know, once you finish your model, you need some data. You want to compare your model to data, and then every once in a while you find that there is no data that's really suitable. Or I heard this nice story of the missing canopy height, and so so it's really nice if the modelers from the beginning of the project are able to say what they want to have measured, where they want it to be measured, and on which basis, how regular. Do we want some co-located measurements to get ideas of uncertainties, and all these input And so in the GMOS project, we have 3 big measurement work packages for ground-based, over water and aircraft observations. And we have 2 modeling work packages for the global and regional modeling. And our institute actually is doing aircraft measurements and regional modeling, so this is where I will focus my talk on the atmosphere. And this is what GMOS is now about to achieve, is a real world-spanning global observation system for mercury, including very important the red dots, which are sites where we measure all the mercury compounds, the oxidized mercury, the particle-bound mercury, which is really difficult to observe, difficult to measure. And you see we have interesting stations like Amsterdam Island. Actually, most people never heard of it. It's equidistant to Africa, Australia, and Antarctica, so I think it has more cows than humans living there. And twice a year a ship will arrive there. So it's stations like this that are quite difficult to maintain or to set up. We have a station on the base camp of the Mount Everest, for example. We have a station on Dome C, which is a 3-kilometer high mountain in Antarctica. And you see, we're really trying to get a global picture of mercury, because if you would, I didn't include a slide, but if you would ask which measurement stations do we have until now, it's one here, which is until last year the only measurement station for the whole southern hemisphere. And we had one here in Europe, and we had a few in the US, but basically we had no information about the oxidized species in the whole southern hemisphere, in the whole of Asia. So we're really clueless what our models are doing and if it's realistic. And just because I think data you don't see doesn't exist, I want to show you our stations. They actually started measuring last year, and we're now getting the first results, and they're really excited if some more time passes and we got some long-term data sets to stress our models and find out more what's going on.
Excuse me, what is the temporal resolution of measured data? It's very
yeah, that's a good question. It's for the elemental mercury, it's hourly, and for the speciated, we use 3 hourly samples. So we accumulate for 3 hours, and then we get a detection limit of 0.4 picogram. So that's already quite high temporal resolution. And later on, I also will show some results of comparisons to diurnal patterns, which is really interesting. And yeah, besides this, we have in red, you see cruises that are performed, and in blue, you see our aircraft campaigns. And the 2 aircraft campaigns we have is that on the one hand, we had this nice casa, which is basically a container with wings, but we had the opportunity to get some vertical profiles and to do some experiments inside the planetary boundary layer, and I mainly included this slide to show you, even here the modelers had a chance to say, we want to fly here, we want to fly there. That's really amazing. And we have a measurement container on an Airbus 380. It's a Caribbean project. They measure a total of, it's almost 90, they measure, basically they measure everything. I put in more than 80 substances, and they do intercontinental flights once per month from Frankfurt and back, and so we have about 5 million kilometers of flights with data for the lower stratosphere, upper troposphere. So you see we have lots of data, and here's just one comparison. What you can get out of this is the measurement from our German ground-based station. You see the measurements from our tropospheric flight up to 3 kilometers. And on the same day, we had the Airbus passing above us on 10,000 meters. And it's really amazing getting these profiles and getting data like this, which really enables you to look at really new things in your models. And yeah, that far for the advertisement for the GMOS project, which you see I'm really convinced of. And now I'll start to show you some of our modeling results. Starting with the atmosphere, we're using CMAC. It's not a newest version anymore. Last week the new version came out, so we're not that fast. But as I said, we're doing regional modeling. So here we've been focusing on Europe with these nested domains I'm showing here, and we're using meteorological data mainly from the Cosmo model, which is a German climate version of the German Weather Service meteorological model, and we're using WRF. we're using different boundary conditions from our global modeling work package, and we're using emissions from AMAP and then refined emissions we do ourselves with our European smoke module. And the data we had at this point, because as I said, all these measurement stations, they've really just been set up and started to measure and started to grow up and find the first problems, repair the first errors. So at this point, we had data from our North German station, as it's just been shown from the vertical profile, where we do the 3-hourly measurements for the oxidized species and the hourly for the elemental. We also do the weekly deposition and precipitation measurements, and we have many secondary parameters to look at ratios with reactants we assume to be important. And you see the black dots, these are I think 24 measurement stations for deposition from the AMAP measurement, AMAP observation system. So here we have monthly wet deposition observations in rural areas. And here I want to show you a first result. This is our model versus the observation of the elemental mercury. And one thing you can see here, and that really is the reason why there haven't been many mercury projects for more than 10 years, it's because we can easily model the elemental mercury. We have a hemispheric background between 1.5 and 1.8. It really is a global background, and we can model it since the 90s. And so many people are saying we can model mercury, mission achieved, no more projects. But now finally that we have the systems to measure the oxidized species, which really have only been introduced for 4 or 5 years ago, I think, we really have now the data to look at the other species. And just to make sure you know what kind of statistics I do, I'm doing bias and error for every pair, and not just here.
Was that forecast or analysis?
That is an analysis. It is for 1 year. It's for 2009. It's hourly data. So that's our hindcast, so to say. So just to check whether our model is as good as it's supposed to be. And right now we say you should be able to model the elemental mercury plus minus 15%. That's the goal to achieve, and that's what we can do here. And yeah, just do it because many people just show the bias for the average, and having all this hourly data, I find it important to look at bias and error for each observation measurement pair, not just on an average. And I start here with the particle bound mercury. And so our first observation is, okay, first try, not too bad, but we see a big gap in the summer, a big large overestimation here. And so we've been really doing very, very basic studies at this point, just starting to look into it. We looked at the different sources of mercury, and for example, we looked if we use only the emissions, or we looked if we use only the oxidation or the boundary conditions. And basically what we find is that our model tells us what is currently assumed in models, that oxidation of mercury leads to particulate mercury, seems to be a wrong assumption, because this overestimation of mercury in summer really comes from the oxidation, and our observations would say this doesn't take place, because if you look at the blue line where we say the only source for our particles, the primary emissions from many power plants in Europe, we get an extremely good agreement with our observations. So this would be some kind of hint that really the oxidation doesn't play a role for the particles, but the emissions are important. And as I said, we've been looking at diagonal circles because I think that's really interesting, because all the reactions we're looking at, they might concern different substances, but they are all somehow related to photolysis. So if you have a daily cycle with sun in the noon and no sun during night, and we have high enough resolution in our observations, we should be able to look at this. And we really see, if we assume, you see in red in model and in 3D observation, you see our observations to suggest there is no diurnal circle that would fit to a photolysis-based oxidation. So that's really for us a hint. And now we can imagine a modeler goes to the measurement community and says your measurements are wrong. because the emissions data we use, they are based off measurements done at a stack level. You're doing it wrong at the stack. Your measurements are wrong. I saw it in my model, and then they start laughing. And so what we actually did is, I'm sorry, I have the slide. I have to skip to the slide. What we actually did, where is my slide? Here it is. What we actually did is, we went with the aircraft to the third largest mercury source in Europe and circled through the plume. You see, we really convinced our pilots to go through the plume, and we could just find that the assumption that lots of the mercury is oxidized and not particulate in the emissions, the assumption is just wrong. I mean, we don't know why. Maybe it's because the plume cools down, and then all the oxidized mercury sticks to the particle. Some say it might be the sulfate, there is some kind of reduction process. We don't know the reason, but we really can prove with these measurements that the mercury coming from the power plant is particulate or elemental, but it's not oxidized. I'm sorry for jumping over all those slides. And yeah, we're back in pace. And then we did the same analysis for the oxidized mercury. And here it became really wild because we see we overestimate the oxidized mercury by a factor of 14. So it's really no more, there's really no connection between the model and the observation. And as I said, after we've been flying through the plumes of the aircraft, and we just said, let's assume there are no emissions for oxidized mercury, and we have only the chemistry going on, we see that we have a really nice agreement between the model and the observation. And also, if you go further and we look at the diurnal cycle, here during winter we're really at the detection limit. I told you 0.4 picograms, so that's just some random scattering. But if you look at summer, our in red modeled and in green observed diurnal cycle of oxidized mercury, it's really fitting so perfectly that we're quite sure this is a sign of some kind of oxidation that's related to photolysis. And from there on, we went to test different chemical reactions. We tested ozone, OH, H2O2 reactions. And what we haven't done yet, but what really is our goal for this year, is to implement bromine chemistry. But so far we could find that, for example, the OH reaction, which is very much disliked, as I said at the beginning of the talk, it really is not able to explain high concentrations of mercury during winter. And the ozone reaction gives us quite good agreement, and the only time when the ozone reaction doesn't work is when we actually overestimate ozone in the model. So that's what you would expect. So in all those times that we get the ozone concentration right, we also get the mercury right. And so yeah, this is the first idea, but we really need to look more at the halogenated species here. But the results for us are really thrilling because now we have these measurement stations that do measure the substances and also the secondary substances, and that's a big problem with bromine. Nobody really measures it, so we'll have quite some problems doing this. But we're quite sure now, we're actually positive there are no emissions of oxidized mercury, and we're quite sure that it's produced by something that's somehow related to the ozone cycle, or at least to the photolysis. And now we just looked at this for one station in Germany, and I mean, you can always tune your model to do one station perfect. So we of course try to get an independent data set to somehow validate what we're doing. And here's the first results. What happens if we use the original idea how people thought mercury would behave in the atmosphere until recently and compare this to our new formulation with new emissions and new chemical reactions? And basically what you see, these blue dots show you that this is the vector position. It's that you have, in these source areas, you have up to 80% less vector position. So it is a huge change just by changing the emissions from oxidized to particulate, from changing the chemical reaction from OH to ozone. We have this large change, and then we looked at all these EMAP stations I showed in the beginning. And I've been doing this scatter plot. You can see that's the concentration bias. So as I told you, we've been strongly overestimating. So everything is right of this line is overestimated concentrations of mercury, the oxidized species. Here we have the precipitation. And in the color bar, we have how well we reproduce the vector position. And ideally, we don't have lots of green dots inside this square here. But what you see is we get things like this, 4 times overestimated concentrations, but we're missing 75% of the precipitation and somehow magically the errors just correct each other and we get a good deposition, but for the completely wrong reason. And if you compare this now to our new model formulation, you see that it's really giving a much, much better picture. We get all these wonderful green dots in the square and we had a party after that. And so we're looking forward. We're really excited having good new ideas about how mercury behaves in the atmosphere. And I hope you still bear with me, because that's not all. We're also looking at mercury in the ocean. And that's where it becomes really interesting, because almost nobody looked at mercury in the ocean. There are a few studies, of course, and it's been done, but there's very little knowledge about what the mercury does. So again, you might remember the slide, we start from the same species. You say we have the dissolved elemental mercury, which here on the right you see was the most important species in the atmosphere, and in the ocean it's just the other way around. The elemental mercury represents the smallest fraction of mercury in the ocean, and here the dissolved and particle-bound oxidized mercury are the most important, the species with the highest concentration. So we just thought we take the same model formulation we used in the atmosphere and we try to adapt it somehow to an ocean model. And we used an ocean model which was originally developed in Hamburg, the Hansen model, and is now further maintained and programmed at the University of Bergen, the Oceanographic Institute in Norway. And our model area is the North and the Baltic Sea. It's a quite interesting model area because it is a high biological activity. And also you see, for example, at this point, the Docker Bank is just 30 meters deep. Here we have regions, oh, my pointer gave up. We have regions here where we go up to a kilometer depth, so it's a quite interesting location, and our benefit here is because it has a fast replacement time. We don't need several hundred years to get our model, to spin up our model, but we can really spin up the model within a decade or so. And so we have a complete three-dimensional Eulerian model representing these two local oceans, and we have what has been done in Norway in the implementation for the biology. Yeah, I'm sorry, chemistry is a lot, but now I'm starting with biology. That's really too much, and I thank you, you're still listening. But it is amazing. We have a strong phytoplankton production in the spring, followed by a zooplankton production, and later on, which is currently just being implemented, fish feeding on these. And all these biological agents, they are accumulating mercury. Phytoplankton and bacteria can actively reduce mercury and to its elemental form, or they can lead to a methylation of mercury, creating the highly toxic methyl mercury, which is then accumulated in the fish. And so we're quite proud having this model with all these processes in. And okay. And I just give you a short introduction what we implemented into the model. So this is basically what we've been talking about, the mercury chemistry in the atmosphere, the gas phase and the aqueous phase mercury. And we had the ocean model with all the biology, the phytoplankton, the zooplankton, the particulate organic matter, which is basically the dead animals and plants sinking. We have the dissolved organic carbon. We have, of course, the oxygen uptake. We have a complete nutrition model with phosphorus, silicate, and nitrogen to simulate the feeding of these species and the chlorine concentrations. And what I've been doing is implementing our mercury species in the ocean and in the sediment. And then one very interesting fact is that we have this reaction with chlorine, where some of the mercury is really taken out of the system, which is a very, very stable complex that doesn't really react anymore. So this is a very important how to say, like a buffer for mercury in the ocean. We have implemented the partitioning coefficient between particles and the dissolved phase here. And of course all the chemical reaction. And basically what we have is a photolysis that goes in both directions, but mainly leads to a reduction. We have during dark, so in deep water or during night, we have a dark oxidation. And in the presence of organic matter and bacteria, we have a biological reduction, which of course is quite problematic because the reaction rates are completely unknown and the ranges are huge. So there's really much to parameterize, so we don't really know what's happening. And even worse, it's if we implement methyl mercury, because here it's not even sure why it's methylated. Some say it's a bacteria, others say it's an active detox system of the phytoplankton. It's really, yeah, it's really more like a game. We're trying. We're looking at the literature and seeing reaction rates that are completely different and are just testing what does it mean if you have this reaction rate or that reaction rate. We're currently also using the oxygen, where we assume that in anaerobic situations we would have a methylation, and if you have enough oxygen, then it would demethylate again. And finally, the methyl mercury is able to accumulate in our biota. So you see that's quite a lot we've been doing, and so these slides, it's really just very preliminary. We're really just still doing sensitivity runs and looking at the model, but the first thing we did is we plotted averages against measurements, and it looked horrible. And then we started looking at the measurements, and we had a total of 2,400 measurements for 10 years, and we found many of them were below the detection limit, many were in rivers or in estuaries, many were just odd because someone put in the cruise number or the altitude instead of the concentration. So we ended with about 700 measurements, which seemed okay. And we were quite startled because we saw in the atmosphere there is a variability, but it's generally not that large if you're not directly next to a source. But the measurements suggest that we have a variability of a factor of 10 if you measure at the same point in different years or different months. And so we've just been looking at some of the stations, and the reason this picture looks so bad is because we have an average from the model over a year, and often we might have just a single measurement. So one example is this measurement in the north of the North Sea. You see we have one measurement here, and I just plotted it just because I was interested. I plotted it for every year we run the model, and you can see how strong the variability goes. You see here in winter, where we have lots of storms and resuspension processes, where mercury that deposited the year before comes back into the water column, and we have this big peak. You can see here a few peaks in early spring, where we have biological production, and then as the year passes, the biota dies off, it sinks, there is deposition, and the mercury concentrations go down again. And just when they've been measuring in August is one of the moments with the lowest concentrations, and afterwards in autumn and winter again we have the resuspension in the windy time, and we've been quite surprised how well we tend to hit these measurements. And it's not just this, there are so many examples. You can see here they've done 3 measurements, and in August they measured something about 1 nanogram, and then in December they measured up to 8. So there's huge variability, and we've been really pleased to see that our model, which really is a first guess and the first, yeah, it was just the first try, why not try it? But we never expected to get this variability in such high quality. And I can just go on, show some of these pictures, because I like them so much, and in the last weeks I've not been doing anything but looking at all these pictures. But the thing is, we do get some more or less regular annual cycles, which involves, as I said, the biological production, the sedimentation, the resuspension. Also, if you're near the continent, you can have a strong input by rivers, which are much stronger input in this area than the atmosphere is. And
this is surface sample or surface sample?
This is, I'm only showing surface samples here. I have one slide on the vertical profile. But what we are now really fighting with is stations like this. For example, in the Baltic Sea, it seems that our model has so very little concentrations compared to the observations. And it's really no way to say, you see, these two measurements, we hit those peaks. So it's difficult to say, because if you talk to the people doing the measurements, they say, yeah, the concentration should be between 0.3 and 0.5. That's what we measure. But our model says, yeah, there are some peaks, but mostly it's much lower. And of course, this could be just wrong. This could be right. There's no way to test this. And the other station from the North Sea was just the other way around. Our model suggests much higher concentrations most of the year, just not during these 2 or 3 measurements. So this is a really interesting thing, and I guess our only chance is to get more observations. And yeah, I'm already coming to my final analysis. We also looked at the vertical profiles. And especially in the Baltic Sea, you have deep basins, and we found, yeah, we're not getting them at all. And the reason really is because we're doing a spin-up from a clean North Sea, and in reality, there have been hundreds of years of pollution, and the ocean floor is highly polluted. So just last Friday, I started the first run. They introduced some polluted sediments in the start, and you see that really could explain why we're not getting these vertical profiles. So we now need to look how to properly describe the system, and already polluted system, because there's no way we're doing a several hundred years spin up with a model that complex. That just takes a bit too much computational time. And now I want to close this session with one last result. We're doing methyl mercury. We implemented methyl mercury in the ocean, although no one really knows the chemical or biological processes, how it's created. But one big question is, why do we have some fish that are highly polluted with mercury, and from the same region, from another month, or in the same month, from another region, we have fish that are completely unpolluted and healthy to eat? And our aim really is, on the long scale, to get some answers, to find some pathways, how we can describe where fish are likely to be more polluted by mercury, and where they are likely to be less polluted. And if you just look at this slide, and I didn't put any unit here because that's just an arbitrary formulation of methylation, but you can see that there is a methylation potential, and for example in this northern part, and those two are really areas where a lot of fishing is going on. You can just see that the methylation potential can be quite different, and so our colleagues from Norway are now working to implement fish into the model, so we actually have animals moving in the system, and we can model, hopefully we get funding for this, to model the uptake and the accumulation of mercury in fish. And with that, I'd like to conclude the session and hope you have some questions.
Questions?
I'm curious about this last thing, how you handle the fish in the model.
Oh yeah, that's actually, the theory is that the fish will go where the food is. So if you have the zooplankton, the fish will just go to the nearest source where they can find food. That's how I understand how the biologists do it, but I'm not an expert on this either.
Their objects are just a consequence of the
I think when they're larvae, they are more like passively transported by currents, and then there seems to be, I always also ask this question, how are you going to do this? And there is some knowledge about where feeding grounds are, and then they just say fish are so clever, they find the nearest source and that's where they feed. But of course, you never know, that's a big question mark.
More questions?
We noticed the found these measurements of Iran group from Italy, with ships. Are you planning to use this data? Because there are interesting results for Adriatic, where mercury concentration seems to be very high in this result.
Yeah, last year when we had this aircraft campaign, it was just 2 weeks before there was a cruise of the MS Urania. And now we started what we call a mercury modeling task force, where we actually managed to invite almost everyone doing mercury modeling in the scientific community, and we just this April we agreed on a set of common experiments, and there we will include the uranium cruises in the Med Sea, and we will include our aircraft container. So that will be interesting.
Are there any investigations related to lakes? To lakes?
To lakes. Oh, there's been done a lot, and the interesting is every publication comes to another result. It seems every lake is a unique system, and especially if you look at the methylation, I've seen methylation rates from 10 to the 30 to 10 to the 5, so it's like billions of.
Also, I noticed that when we discussed diurnal variation with the model distribution, we saw in particular matter concentrations also in model, two maxima, which are related to activity and suspension traffic. But this will be the case in mercury variation.
And the thing is that the oxidized mercury is quite fast to deposit, so I think that we assume that it is a local phenomenon, now that we are sure that it's not directly emitted. And if you have re-emissions, they are usually in the form of elemental mercury.
But I mean the suspension from the road, for example.
Yeah, but the thing is that usually we assume that it gets reduced before it really resuspends. And if it's, I mean, okay, there's something like wind-blown dust, and our current assumption is that it's quite fast to deposit again.
No questions?
So in the middle of your presentation, you showed simulations of mercury or Europe, and then your boundaries curiously had continuous maximum, and the minimum was somewhere in the same.
Oh yeah, that's because what I've been showing was only the difference between the runs, and the boundaries were completely dominated by boundary conditions. So that's really what I can go back there and show it. That's really what we want to see, because that's too far. You really see that's what we did here is mainly change the emissions, because we found that oxidized mercury is not emitted, so we find a difference near the sources, but we did not change the global model, so we get the same boundaries. So basically it means you're here at a 1, that means there's no difference between the runs.
One more question. When you see such uncertainty, considering in the future some ensembles looking into uncertainties in atmospheric model and the ocean model, and also the coupling between them.
So in the atmosphere, it's definitely what we're doing. The problem really is that the project is now running 3.5 years of a total of 5, and the measurements, it took so much effort and time to set up the measurements, and the mercury measurements, they are, I'd call it semi-automated. You really need personnel that knows what they're doing. It's not just activated. So of course, the first years of measurement, we had lots of problems with all the different groups around the world. And so we're finally getting the data, and that's the reason why we started this mercury modeling task force, because we want to do exactly that for the atmosphere. But for the ocean, there's so little modeling in the ocean. I know the Geofizički group, they have a slack ocean where they have a surface ocean model, and they use the biological data from chlorophyll satellite measurements, and some models do have some formulations for the air-sea exchange, but really ocean modeling of mercury, it's just starting. So I'm not aware that anyone really used the full Eulerian model to do any modeling in the ocean before.
For the CMAC model, how good chemistry for the mercury, in your opinion, how much work?
Yeah, the problem is that the last work was done by Russ Pollock, I would say end of the 90s, beginning 2001-2, and they didn't have any measurements of the oxidized species, and what people did is they analyzed the weather position. And the big problem is that the models really like to underestimate the precipitation, and they completely overestimated the oxidized mercury. So if you go back to 2003-4, you'll find lots of papers that say we're doing perfect job on the weather precision, everything is fine. And then really a few years ago, when we had the first observation of the oxidized mercury, it was when people found out it's just errors canceling each other out. And yeah, now what we need to do is to get bromine reactions into the model. That's really what we need to do. And also to your question, the coupling, currently the ocean model, it's not fully coupled to CMAX. So because we're doing like 20-year runs, 30-year runs of the ocean model, and with CMAX that's just so expensive that currently I use 1 year of standard atmosphere and couple it to this, because otherwise you couldn't do all the sensitivity runs. So we want to have it fully coupled once we find a final formulation for us.
What about other heavy metals like cadmium compared to mercury?
So we are only doing mercury, but that's really the thing is with all the other heavy metals, they have one thing in common. They have a zinc. For example, cadmium and lead. Once it's deposited, it usually stays there. Maybe if it's in the tropics, it might hop once or something like this. You might have a limited grasshopper effect, but generally these are substances where you have a zinc, and it's really mercury that's constantly, once you have a zinc, then it's reduced by some bacteria or by photolysis and other reactions, and then suddenly it's there again. I think the closest we have to something like a zinc is that we have a strong accumulation in the Arctic, but besides this, it's really just, it's so volatile and so moving, so it's the most interesting of all the heavy metals.
Okay, if there is no any more questions, I would like to thank you again.
Thank you.